All right, so at this point we've talked about trig functions in terms of the unit circle, triangles, defined them as functions, talked about certain properties of them. Then we talked about them as functions. And once we have a function, we would like to be able to work things backwards, which means talking about the inverse. So we're going to try to talk about the inverse of trig functions today. We're going to focus on the sine function, and then next video we'll focus on the cosine function. Before we do that, I want to start off with an example, just motivate why we work with inverse functions and what they are and how we can use them. So let's start off with a question. So for example, we can ask if 7 equals 3x plus 1, what's the value of x? Now we could subtract 1 and divide by 3 and go through and do the algebra to work with this. Or we could do this. I can define the right-hand side as a function, and then if I can find the inverse of that, I can then take the inverse function evaluated at 7, and that'll give me the value of x that works with this. And everything's okay with this, because if I were to look at this function g, it's a linear equation, like that, it's 1 to 1, so for any given value of y, then there's only going to be one value of x associated with that. So if you give me a value of y, there's only one value of x that's going to be that's going to give me that value of y. So it's a 1-to-1 function. I can define the inverse, and everything is fine. So let's see. So what is the inverse? So I start off with this relationship, and I solve for x. So the first thing I'm going to do is I'm going to subtract 1 from both sides. Once I do that, I'm going to divide both sides by 3. And now I've got my inverse function. So if I let h be the inverse function, right, so this is going to be, what, 1/3 minus 1 plus y. Oops, and that's not an x there. I'm defining it in terms of y. Okay, so this input has to be consistent with my formula. So what does this mean? This means if I take h of 7, I'm going to get the value of x that will satisfy that. So what is this going to be? 1/3 minus 1 plus 7. So let's see, 7 minus 1 is 6. Which gives me the value 2. And if I plug in x equals 2 here, I'm going to get that. Okay. Now this is kind of a trivial example, and it's not all that useful, but being able to work with this in terms of an inverse function allows me to look at this in a more general framework and say, for any given value here, what do I get out of it? Okay? So let's turn this around and ask a different question for a different function. In particular, suppose I know that square root of 2 over 2 is equal to the sine of some angle. And I want to find the angle that's going to satisfy this. Okay, so we immediately run into an issue here. And if I go back to the unit circle, think about this. What do I have? So I'm looking for the point here. Okay, so I happen to know that when theta is pi over 4, that it's going to give me, the associated point is going to be that, and because it's sine, I need the y value to be equal to that. Okay, so this says then that theta must be pi over 4. Okay, but there's a problem. The problem is if I were to take a horizontal line here for this given value of square root of 2 over 2, there's another point on the unit circle where the y value is the same as that, and it happens to be in the second quadrant. And notice that the reference angle associated with this angle, so we'll call this angle psi. The reference angle associated with psi is pi over 4, so what is that? So that means if I go over psi plus the reference angle, I will go over a half a revolution, which is pi. So that angle is 3 pi over 4. Okay, so what's the angle here? Is this angle going to be pi over 4, or is it 3 pi over 4? I can't tell the difference. To make matters worse, I could go over here and I could go around one whole revolution. So I could go to pi over 4 plus 2 pi to get that. Or I could go to here and take one revolution around. So another answer is 11 pi over 4, and I can just keep doing that over and over and over again. So there are many, many, many different angles that are going to give me a solution to this equation. So I've got a problem here. Okay. So let's back up and think about this in terms of functions, see what's going on here. So if I think of the sine function, if you give me a value of y, so in this example, what did we have? We had square root of 2 over 2. Then there's all these different values of theta. Right, so this is what, pi over 4, 3 pi over 4, this is going to be my 9 pi over 4, 11 pi over 4, and blah, blah, blah. There are many, many different values of theta that are going to give me that value. And so the issue here is this function is not one-to-one. Okay? So because it's not one-to-one, we can't find an inverse. So the question is what do we do? Okay, let's back up again. So one thing to notice is we've dealt with this problem before. We've worked with functions that are not one-to-one, but we found a way to find an inverse by playing games with domain. Okay? What was that example? If we look at y equals x squared, we cannot invert this thing. Okay? So for example, if I ask if 4 equals x squared, what is x? I'm going to get two answers, either 2 or minus 2. Okay, and what's happening here is, so if I go to 4, and there's two different values there that are going to work. Well, we have this thing that we call the square root that inverts this, but it doesn't actually really invert everything. What it does is we said, well, let's just restrict the domain so that we only work with values of x that are not negative. Okay? So in this way, if we only worry about this side, right, so we can just assume that the value of x is positive, then it is now a one-to-one function. I've only got this branch, or that part of this parabola. So if you tell me that 4 equals x squared, I can say, well, let's let h of x equal x squared, g of x be the square root. Okay? So this is saying that 4 equals h of x. If I take g of both sides, then by composing these, because this is the inverse, and I'm assuming x is greater than or equal to 0, I'm going to get x. And now this is saying that x is the square root of 4, where x equals 2. Okay? But what happened? We know that we pulled off this trick where we cut this thing in half. Right? We always keep this in the back of our mind, and we know that we did that. So what we do instead is we recognize that it could have come over here as well. Right? So that's why we always do this plus or minus, it's because we knew we pulled a fast one. Okay? So we're going to do the exact same thing with the sine function. So what are we going to do with the sine? Sine of theta, sorry. All right, so to plug in values of the sine, which are going to go between minus and plus 1. Right, so if you give me a number between plus or minus 1, I want to be able to just get one value out of here. And what's going to happen is I'm going to need to just use some value of this curve as it goes from plus or minus 1 in terms of the range. I could use this. Okay? I could use, it's from here to here or from here to here. There's many, many choices I could use. The issue is we have to agree on one thing and just stick with it, so that when we go to a calculator and use this and find the inverse function, we can all agree on what it means and attach a real meaning to it. Okay? So what we do and what we've agreed upon is that we're going to go from minus pi over 2 to pi over 2 and restrict our domain to be from there to there. Okay? So by doing that, if you give me a value between minus 1 and 1, I'm only going to be focused on which value of theta between here and here, is going to give me that value. So essentially what we're doing is we're basically ignoring everything else. Okay? So by just focusing in on that, we can figure out what's going on here, and we can actually go through and define the inverse on this. But then when we use it in practice, we have to go back and remember, oh, we erased all that other stuff. Okay? So how do we do that? Just a quick note, in terms of how do we attach meaning to this. If I go back to the unit circle, if I look at angles from minus pi over 2 to pi over 2, I'm basically looking at angles that are going to give me points on the unit circle around here. Right, so this angle here is going to go from minus pi over 2 to pi over 2. And in terms of the sine function, I'm only going to be working for values of y from minus 1 to plus 1. Okay? So how does that work? Okay. So let's do an example. Suppose I want to know what's the inverse. I should be careful here. This is new notation. The inverse of sine is I'm going to define that to be the arc sine. Okay? So if I ask, what is this? This is saying I want to find the angle where square root of 2 over 2 is sine of theta. Okay? So these are equivalent statements. So the way to think about this is if I start with this, I now compose both sides with the arc sine. Okay. Now, I'm assuming my value of theta is between here and here, so this is very important. If I assume that is true, then when I take the sine of this angle, I'm going to get a value of y, and I can find the value of theta associated with that. Okay? So by definition of what it means to be an inverse, the arc sine of the sine is going to give me theta as long as I've restricted my domain. Okay? And this is going to give me the angle between minus pi over 2 and pi over 2, where the sine is square root of 2 over 2, and that value is going to be pi over 4. Okay? And now I've got to figure out what are all the other values, so now I go back to my unit circle. So I know that when I get pi over 4, the y value associated with this angle is going to be square root of 2 over 2, and to figure out the other angles, I can just figure out what other points on the unit circle have the same y value. It's going to be this angle here, and notice this has to be the reference angle associated with this. So if this is the angle psi, then psi plus my reference angle equals a half revolution. So I get that value. Okay? And now I can go from here and here use those two numbers and add 2 pi, subtract 2 pi, add another 2 pi, subtract another 2 pi, and I get all of my solutions. And let me do one last example, and we'll call it, okay, so for the last example, I'm looking for an angle. It's got to be in the second quadrant. It's going to be between 0 and 2 pi, where the sine of the angle is 0.2. Okay? All right, so now because this is positive, it makes sense to talk about what's going on in the second quadrant. Okay, so let me adjust this picture. So the y value is 0.2. I'm looking for that value there, so I don't know what that x is. I know the y value is 0.2, and I know that point there. Okay? Since it's in the second quadrant, I know that I'm going to be working with that. So there's my angle theta. The problem is now if I take the arc sine of both sides, and this is, my calculator is going to assume this angle is between minus pi over 2 and pi over 2, so it's going to think it's in the first quadrant. It's going to give me that. So that's really quite not quite the right answer. So if I calculate this, or put this in the calculator, I'll get some number, but it's in the wrong quadrant. Right? So it's going to give me this angle right here, and that angle is the arc sine of 0.2, and it's going to have, that's going to be my reference angle for the angle I'm looking for. So let's see, that tells me then that the angle I want plus the arc sine of 0.2 has to give me pi. Right? So this is the angle theta that I want right here. And if I plug that into the, if I solve for theta, I get that. And if I plug that in the calculator, I get about 2.94 radians.